Hello everyone, hope you're doing well. Today we'll go through system design fundamentals. So let's get started. Just give me a moment. Okay. Okay, here we go. So we'll talk about fundamentals today. As we progress in this series, we'll cover other aspects in more details. But yeah, let's get started with the fundamentals today. So when we talk system design, essentially we're talking about these things, right? So we'll cover what system design is, what are the core principles behind that, which we should take care of, what scalability patterns looks like. Again, today we'll cover at a high level, and as we progress, we'll take each of these into greater details, and that will help you to understand in more depth. But today, let's try to get an overview, followed by database strategies. So which are the things which really matters, and how we decide on some of those trade-offs. Caching, again, is very important. Load balancing, yeah, as systems are getting more and more distributed, so load balancing is crucial. Then we talk about architectural patterns, which again will not cover in greater detail, but certainly we can talk few key points around those. Distributed system patterns, again, which are really important as systems are getting more and more distributed. And we'll talk about some design trade-offs as well. You might have heard about cap theorem and things like that. So let's get started. So what is system design? This word is understood by different people in different ways, right? So typically it is for tech architects or technical leads who care about, or who is part of either directly doing that, or maybe they're contributing to along with somebody else. So what is system design? So it is about how you design your system in a given circumstances, right? Sometimes design can be great, but if it is not fitting into the constraint that you're operating, it could be about infrastructure, it could be about budget, things like that, right? So you got to design system which is meeting the needs of the business, or whatever, whichever place you are designing that. There is nothing called perfect design in all the places, because if data, there are a lot of variables there, right? It's about data availability. It's about different system integrations required. It's about team skill set. It's about, again, end of the day, it's all money, so budgeting, right? So all things come together for system design. Essentially, when it has to go live, right? We're not talking about theoretical system design where academically we can talk anything, but in reality, when it works, you got to look into the real world aspects. That's when system design really is about, in a given circumstances, how best you can fit in your technical components for an overall solution, right? That's a system design in practical terms. So yeah. And again, trade-offs are very fundamental things. So you may not get, I would say, if you want to go too far on certain things, you will lose few things as well. So there is always a trade-off, like other aspect in life. System design is no exception. So we'll touch on some of those as well. Okay. So let's go further. So the other principle, we call it, sparse kind of principle. So there are six key aspects where any system, people who is designing system or architects needs to consider. Without that, I think they will lose some other things. They may choose to maybe pay more attention on X versus Y, but they can't totally ignore any of those for a good design. Scalability, certainly, it is about how your system is catering to the growing needs of the business and growing user base, things like that. So scalability, again, there are aspects we'll cover in some detail today. Performance, of course, although systems are getting more and more complex, but you still need to take care about throughput and latency. You can't totally say that his system is complex, so my system is slow. People needs to use it, and for people to use it, they need to get at least decent performance, if not great, though they expect a great. So you got to manage some of those as well, including caching and things like that. Availability, yeah. Uh, and nowadays, mostly it is depend on if you're hosting in some cloud environment. So cloud vendor have their own availability time, up time they call it. The latest is, or the most common is we call it 5 nines, 99.999, and typically if that is people have that kind of time, so it means that maybe 5-6 minutes in a year kind of downtime, right? So it's pretty minimal, and I think that is a that is there for critical systems. But yeah, I think you can choose depending on the criticality of the system, that how much you want to have uptime. And of course, if you go for more, it comes with a cost, right? Reliability, yes. Systems goes with that kind of failures in real world, but the point is that how soon and how easy they are able to coming back to normal. So that is called fault tolerance, right? How quickly are they able to come back to normal, right? So there are different strategies around that. Consistency, yes. Although in modern systems, eventual consistency is kind of getting more traction, but there's still area like finance and all where you can't afford to have eventually. You got to have a strong consistency, right? So all the nodes should be showing the same data. So that is again aspect to look at. Security, again, last but not the least, security is paramount, right? You build anything, if it is not secure, it won't be used. And in the enterprise environment, it becomes even more important that all the aspect of compliance and all that taken care of, security and aspect of that. So okay, now let's go on little more details on what the sixth thing we discussed, right? So when we talk about scalability, essentially we talk about two things: horizontal and vertical. Vertical, let's start with that. So vertical is something that you're not expecting a lot of load over years, or maybe users will grow in a not in a like exponential, but maybe uh, a stable, I would say, growth. It's like maybe every year 5, 6, 10%, right? So you know that it's not going to be 2x, 3x, 4x like that. So if the growth is minimal, it could be about, maybe for example, it could be about some HR systems, or maybe a system that is not expecting a lot of growth, right? So you can still choose to vertical scaling. It is simple to implement. It has less overhead, and it's easy as well for developers to understand and debug and things like that. So don't directly jump into the horizontal scaling, though that looks fancy, but it comes with its own overhead. Okay, so horizontal scaling is designed for a system that is expecting a lot of growth, user base growth, or a lot of uses is going to be there in future. So that you can extend it without any downtime, right? That's the key part. Again, there are architecture which will helpful for that. We'll talk in more details as we proceed in upcoming sessions as well. There are different aspects of scalability patterns and all. So we'll talk more as we progress. Database strategies, again, sharding you might have heard, where we replicate the data across different hardware devices, right? And sharding, we don't replicate, but we store data into different hardware devices. There are strategies around it. And replication is one where when we replicate data across different geos for better performance, typically for read operations. If you talk about key differences, so basically sharding is something that you want to keep maybe a specific, let's say, geo data or country data into one shard. It's like you can assume as a database server or database server instance, and you want to grow as needed. So there are different strategies around sharding as well. But you can't avoid it if the data is really growing exponentially. So you got to have different shards. though it's come with its own overhead about managing. Essentially, there are different instances, right? So you got to the joins and all will be slower, but I think there are some strategies around it which we can mitigate to a large extent. Yeah, and also what kind of data are you putting into different shards is also important. So sharding is there. Replication is of course to improve the read performance. Typically, you replicate your nodes across different geos so that you can get a faster access. Uh, Again, there are some best practices we'll cover in greater detail when we go each topic of each these topics and separately. But yeah, at a high level you can understand that one for extending databases instances depending on different criteria, and extending different database physical, I would say, instances, you can say, to store the data. And second is about copying data into multiple geos for better read performance. So yeah, at a high level. Caching strategies is topic of its own, but and again we'll cover in more details about these. Different eviction policies, different caching patterns. Yeah, but at a high level, you can understand that uh, it is used pretty often nowadays, because since the systems are getting distributed, if you don't use caching, there is no better way to get the better performance, right? Caching can come in different form. It can come in CDN. You might have seen or read about that, how data is put into different CDN servers across the globe, so that when users are accessing, they're getting a faster access, right? So, and there are different CDN providers as well available. It could be about, let's say, any video that is getting popular. So, for example, Netflix can stores that video in closure CDNs so that it gets a faster access, right? So like that, you can assume. Application cache, of course, this for mostly for application performance and how we can have the faster access. You might have heard this term called 20% of the data is accessed 80% of the time. So you got to find what is that 20% that I should use so that I can get the best performance. So that's a strategy. And if you put that 20% data, which is accessed 80% of the time, in cache, I think you're really doing good thing, and your application will have a better performance, right? Again, distributed caches as well, which is there. Redis is one of the popular, I would say, provider there, to kind of speed up the loading and all, right? We'll talk about patterns and which is more relevant for which case as we proceed. But yeah, I think these are things which are important. Different patterns out there, different eviction policies, basically how you clean the cache, right? You can't keep the data forever, so you got to clean, and there are different approaches around it. Um, you know, so yeah, we'll talk about those as when we cover only caching, right? So yeah, we'll cover all that. Load balancing, again, an important topic, depending for especially for distributed applications where data is loading more and more, and users can't just have one server, right, for their I would say data retrieval and all. So, and again, there are two major, I would say, type of load balancer. One for transport layer, in case you've gone to that OSI layer, right? So transport layer is that application is a last layer. So for application layer, load balancer are there, right? Which kind of distributed the load as at the application level, and there are transport level load balancer as well. So depending on the need, you can pick and choose. We will cover more on these strategies once we cover this topic in more detail. But yeah, these load balancer really helps to share the load so that users get, I would say, better performance irrespective of which part of the world they're accessing, right? So these these strategies really help, and it shares the load properly, right? There are different strategies about or policies about, like round robin, least connections, all that, so that not just one or two servers or service instances are getting overwhelmed. Rather, it is shared across different different instances, right? So all the strategies come into picture. There are some health check and failover scenario as well. If some node got down, so how you can fail over to the next one. So all that we'll discuss in more details as we proceed. Okay. Now architectural pattern. So it is again essential in distributed design and application, which are, I think I did cover that, which is, in the first one, I guess, uh, monolith versus uh, you know uh, not monolith, but other horizontal versus vertical, right? So when we talk about horizontal scaling, typically the most closest match is microservices, because that's when you store different services into different nodes of horizontal scaling, right? You will scale horizontal, and you can have that kind of architecture. So high growth, you can take any popular system like e-commerce systems, or wherever you expect, or any gaming system where you're expecting a lot of growth. Those are the good example of either horizontal scaling, and the most complementing scenario or most complementing architecture is microservice architecture, right? At the same time, there are systems which are not that kind of growth oriented, which are like important enough to have it, but it's not necessarily growing the speed like others. So for them, it could be vertical scaling, and the complementing architecture is monolith architecture, right? Simple one which you can manage it with less overhead and less complexity, right? You can also choose that you're starting with monolith, and as users are growing, you can evolve it into the microservice as well, in case you don't have all the know-how to begin microservice initially, because monolith architecture are easy to build. Like, you keep all the code base into one layer, right? And you can do prototyping, and you can show something real quick. Where microservice may involve a lot of deeper design aspect, more complexity, and it is good for large teams, right? And high skill requirements. So don't directly jump into the microservices. Rather you analyze your use case properly, and accordingly you deal with, which is really important for you. Okay. As microservices have evolved, there are different patterns which came in as well, like API gateways there, right? So that you are not exposing all the APIs independently, rather you are hosting, or you providing a platform kind of gateway where you can host all your APIs, and let gateway kind of do all the common concern like authentication, authorization, rate limiting, and things like that. So that way, it is a really, I would say, complementing pattern for microservice architecture. CQRS also, it's like you're designing your read queries and write queries separately or differently. You're not putting all at once. You have different scaling requirements for both read and write. So CQRS again comes very useful pattern for microservice architecture. Like that, you have circuit breaker. Pub sub is pretty popular architecture pattern, which is there since, I would say, decades, if not ages, right? Or a couple of decades. It's not a new thing, right? So you publish something. It's like more of a async communication. Queues you might have heard. So they're pretty, I would say, goes hand in hand. So you put messages in queues, like as a publisher, and let all the uh, customers, you can say the takers or subscribers, of plug into that, and they get the message, right, in a sync way. So you're not overwhelming your systems. It provides you, it's like to avoid the floodgate, in short. Like that, you have other pattern like Outbox and Saga as well, that you can pick and choose depending on the need. Okay. Again, trade-off, pretty known word, I would say, mostly overused, but it is can't be avoided. You got to have a trade-off, right? Because uh, you can't go extremes, and if you go extremes, you will completely lose the other things. So how you balance it out? It's all about balance. Uh, and balancing depending on the circumstances that you are designing system for. So that's when the CAP theorem comes in handy. We'll cover, as I said, in all these in greater detail, but today understand that in distributed worlds, you can't pick all three together. So, when we talk about distributed, basically we're saying that partition tolerance, right? Because we are having a different partition and network nodes, so they're not sitting on the same system. So you can pick either, you can have basically, in short, CP system or AP system. CP means you will prioritize consistency and partition tolerance, or you will prioritize availability and partition tolerance. Nowadays, most application tends to go into AP mode. Availability and partition tolerance means they are okay with eventual consistency, right? They don't need a strong consistency. But there are exceptions like finance or any other, where you quickly need, you can't afford to have even a fraction of second delay on data inconsistency. In those cases, you need to prioritize consistency and partition tolerance, right? You can't have eventual. So like that, you can pick and choose, but you can't get all. That's the point here, that in distributed systems you can't get that, hey, I'm on distributed system but I need both availability and consistency of the same degree. No, you got to compromise one or the other. Or you can say that I need this more or this less. So some trade-off has to be there, and that's depends on, the system. Your application is read heavy, write heavy, strong consistency is required, less is fine. So all that comes into picture. Again, performance versus cost. So it looks fancy to say, hey, I need high performance and all, but when you go for having an infrastructure where those will give you better performance, you say no, no, it's too costly, right? And both are the, I would say, real world communication, right? But the thing is that you got to balance that, how much costly hardware you want to get versus are you okay with this performance, right? So if you really have a tight budget, you can expect a moderate hardware performance. I'm not talking about here code performance. That is other aspect that needs to be taken care of. I'm only talking about infra performance. So for infra performance, it's typically how much you are able to pay for that, right? So because these components come in different uh, layers, like premium, moderate, and low, right? So you got to pick and choose that how much your budget supports. So accordingly, you may expect a performance, right? Complexity versus maintainability. So it's again, I think we spoke about uh, vertical scaling, we spoke about monolith. So you can relate like that. So if you go for, let's say, horizontal scaling, microservices, then you are essentially going for high complexity, because those will be like uh, complex to manage and complex to debug and all that. Versus high maintainability, you can relate with like vertical scaling, you can relate with monolith. They're highly high to maintain. So again, a trade-off that you want, uh, high complexity versus high maintainability. So again, you can't just decide, rather it's about the problem that you're solving. So if it is a high growth system, you can't uh, go just with high maintainability. You got to have, basically, even you don't like, but complexity will come. You got to manage all that complexity. It's about horizontal scaling or whether it's about microservices. So sometimes it's not a choice, but rather how you manage it. Even you are going with that option, right? Latency versus throughput. Again, latency is something that, one instance, how fast it, or one, I would say, instance, or one user, how soon it is kind of getting end to end, right? And again, throughput is like basically how many users are using, and overall how at the system level how fast you are getting. So you need to manage that, this latency and throughput. Sometimes you prioritize the throughput for a system level performance. Sometimes you may choose that, okay, typically is throughput is really, in modern systems, really a good benchmark. uh, Overall, how much, depending on the user base, how much throughput you can expect, versus in a scenario when you want to measure the individual response time. That's okay, but maybe it can give you some hint. But for a system level, I think you should prioritize the throughput as well, or throughput essentially. so that overall at the system level your application is really giving a good result. Okay. Now I think we are towards the end. So what are the takeaways? Trade-offs are unavoidable, right? Inevitable. You need to really look into that, which trade-off is really how far you want to go, right? We talk about 6 different aspects, so each have their own trade-offs. So how fine balance you are looking for. Uh, for that, I think the strategy is that start with the requirements. Go with the requirements, understand that functional, non-functional requirements, and accordingly you derive that, okay, maybe for this makes sense. Um, Proven patterns, yes. There are strategies which have worked over time. It could be sharding, replication, caching, load balancing. So use those, right, instead of inventing of their own, because these strategies have helped people over time. So those are the proven ones. And the important thing is that don't try to perfect at once. Sometimes it goes with iterations. So start simple and grow as needed. In a MVP pattern we call it, right, minimal viable product. Instead of trying to build everything once, try evolve over time. We also call it agile approach. So all that is important. So again, before we close, there's no wrong answer in system design, only the one with that you can't explain it better. So what it means that you should be able to explain what you're doing and why are you doing, instead of good or bad. So that really matters. Okay, that's the end of this. We'll cover as we get these aspects in more detail as we go further. But for today, let's wrap it. Thank you. Take care. Bye bye.